Thank you for inviting me for this keynote. I'm happy to share with you what we learned from our exploration of confidential computing technologies in the past years. But before that, first let me tell a story. A student of mine had complained to me back years ago and about the difficulty in cybersecurity research. In system security research, you have to take months of effort to find a right topic. Then you have to execute. You need to come up with an idea and execute your idea by building a system, by performing extensive experiment, and finally writing up a paper. The whole period could be as long as 6 months for a single student. And the paper is submitted and could also be rejected. By comparison, in other areas, such as artificial intelligence, typically a student takes about 2 to 3 months to come up with an idea, do some simulation, and with some theoretical presentation, and you can get a paper accepted. And if you have multiple good AI paper, you could find a job in today's market. So the student feels so unfair. So what I told him is, yes, and this is the situation today, but you shouldn't looking at what happening today, and you should also look back at the whole history. Guess what? When I graduated from Carnegie Mellon in 2004, half my dissertation is on machine learning, on artificial intelligence. I published a triple AI paper in 2002. I published a NIPS paper in 2003. But when I graduated in 2004, I couldn't find a job using my AI credential. Why? Because it was the end of AI winter. Just because you have a good AI publication does not mean you could find a good job at that time. The reason I end up finding a faculty position at IU is because the other half of my dissertation is on security and privacy. Guess what? In the past 20 years, I've witnessed up and down of many areas. But no matter which area become popular, there's always a security and privacy challenges. There's always a security and privacy opportunities. So security will always be there, but other area, harder to say. But in the meantime, I've been asking myself, what happened in the past 20 years? What happened in the past 20 years that has moved AI out of the woods? What happened in the past 20 years has made AI great again? So in my personal opinion, I think there are two important issues. The first is the availability of massive amount of computing resource. So today, with the support of GPU and other kinds of accelerator, we definitely could train a much deeper neural network than we could back a decade ago. The other important things is the availability of big data. Only from big data we will be able to extract deep knowledge. So what I'm going to say here is big data fuel the AI engine. But down the road, are we going to have more data or less data? If we don't have enough data, the AI engine could be stifled. Right? So we may get back to the AI winter again. So the answer looks quite obvious, right? How could we have less data? Looking at today, looking at what's surrounding us, and we have all kinds of IoT and mobile devices that aggressively collect personal information from us. And even for this conference, I have to produce video, produce some digital signal, produce more data, and to do this remote presentation. But just because we have more data being produced does not necessarily mean that more data will become available for training AI model. Why? Because in the meantime, and we are facing the risk of data exposure. And in the past decades, and we witnessed all kinds of data disclosure. Some is so seriously, which have even affect the presidential election. In response to such a data breach. Countries around the world will come up with different kinds of legal regulations to protect and unauthorized disclosure of personal information. But in the meantime, it also put a limitation on data sharing. So we are facing the dilemma. On one hand, the continuous sustainable progress of AI and the data science require data. On the other hand, people are becoming increasingly reluctant to share data. How to address this dilemma? One solution from the security community has been studied for many years is confidential computing. How about we allow people to use the data without seeing its content? Right? An example is those crypto solution, homomorphic encryption, which allow you to compute any function on encrypted data. And secure multi-party computing allow two parties to jointly compute any function without exposing the data from each party to the other parties. But the problem is those solutions, they are still quite expensive, still orders of magnitude behind any, what expected for any practical use. Alternatively, we're thinking about another solution, which rely on those hardware-based trust execution environment to support confidential computing. An example is Intel's software guard extension, SGX, and the trusted domain extension, TDX. AMD's memory encryption technique, SEV, ARM's trust zone and confidential compute architecture, CCA, and other emerging techniques such as Keystone Enclave, Graviton, and HyperThreading, which I'm going to talk about today. For example, Intel's SGX is a set of instructions for protecting the computing within a memory region called enclave. The data outside the enclave are encrypted and only decrypted when they are moved into the enclave. The computation on the data is isolated from untrusted operating system and even untrusted system administrators. The design of such TE is meant to protect explicit data disclosure during computing, offer strong assurance for data in use protection. However, the operations within TE are known to have side effects that could be observed by the adversary outside TE to infer the content of data. Examples include page table entries for memory protected by SGX, which an untrusted operating system could manipulate to induce page fault within the TE, and therefore observe the page access pattern of the program running inside the TE. Today's TE are not designed for defend against such side channel attack. So the first grand challenge for TE-based confidential computing is how to control the side channel risks. Although the microarchitecture side channel have been extensively studied, existing solutions are mostly whack-a-mole approach, trying to address a specific risk without considering the impact on other related security risks. In our research, and we're trying to find a different solution, a solution that not rely on analyzing of a specific attack, but we're looking for some common necessary condition for a set of attack. If we could identify those set of such a necessary condition, and if we can effectively remove that necessary condition, we could shut down a large attack surface for many attacks. And this will provide a better solutions in our opinion. And our preliminary research found that this is completely feasible. Back 5 years ago, together with my collaborator at Ohio State University, we extensively inspected memory-based side channel vectors on SGX. Our research showed that most of known attack need to trigger interrupts. For example, page fault, TLB shutdown. Those interrupts could be observed by the program running inside an enclave through an asynchronous enclave exit, which is called AX. The only exception is that the attacker who can leverage the HyperThreading functionality of today's Intel CPU and could launch a stealthy attack to silently monitor the operations happening inside an enclave without triggering any interrupts. So HyperThreading is Intel's proprietary implementation of simultaneous multithreading. It enables a single physical core to execute two concurrent code strings called hyperthreads. Each thread will running on a separate register, so they have two sets of register and within one CPU core. But those two threads also need to share some execution resource, such as a cache, branch prediction unit, and translation look-aside buffers. So running inside this enclave, a malicious thread could silently monitor a legitimate and an enclave thread by leveraging those shared resources to find out the side effect of the enclave thread's operation and on those shared resources to infer what happening inside the enclave. So in our research, to address this problem, we come up with a very simple idea. And because what we are afraid of is attacker can run a malicious thread on the CPU core that executing an enclave thread. So how about we run two threads, both from enclave, side by side, fully occupy a CPU core. So if we could do this, then we will completely shut down the attack surface. But this is non-trivial because the operating system is in the hands of a malicious party, right? To address this problem, we come up with a simple idea. How about we could allow both threads running a colocation test at the beginning of the execution. If the colocation test passed, both threads believe they are running on the same CPU core. Then the only thing it needs to do is they can continuously monitor the occurrence of asynchronous enclave exit. The occurrence of AEX means the malicious operating system could switch one of the threads out of the current CPU core and move it to a different CPU core, right? So when this happens, both threads need to run colocation test again. If this time it fails, then they will terminate and no longer touch sensitive data to prevent information leaks. Right? This sounds like a simple and elegant idea, but to make it happen, the most important things we need to do is how to do this colocation test, how to design a practical and also efficient colocation test. So and we come up with a very simple idea. We leverage risk condition. So risk condition is a bad thing for parallel computing, but and we turn it into a good thing to help us to effectively and efficiently identify any malicious activity the operating system can perform on the enclave thread. Right? So we are using a contrived data risk for the colocation test. So the idea is very simple. And we run two threads from the same enclave, right? And both threads operate simultaneously on a shared variable. This variable also inside the enclave, so its content couldn't be changed by the malicious operating system. So, and the simplest way to do that is one thread called protect thread continuously write 0 to the variable and wait for 10 circles, and then read from the variable. Well, the other thread, which we call shadow thread, will continuously write 1 to that variable. If both threads are running on the same CPU core, they communicate through the L1 cache, which is very fast, as efficient as an execution of a single instruction. So that means, and because the protect thread writes 0 to the variable and need to wait for 10 circle, right? Well, the shadow thread continuously write 1 to the variable. So so after 10 circle, when the protect thread read from the variable, it's most likely the thread will find out the content of the variable is 1, right? But on the other hand, if both threads are running on 2 different CPU cores, right, and to play the same game, these times no longer they can communicate efficiently through L1 cache. The communication needs to go through a cache coherent protocol, which takes 190 circles on the Skylake system. So if the protect thread writes 0 to the variable and wait for 10 circles and read it out, the content may not be synchronized to the other core. So most likely it will find out the content itself written to the variable. So the chance of finding out the value is 1, which is written by the other thread, will be very low. So based on this idea, we build a simple and elegant collocation test. And the real test is a little bit more complicated than what I just introduced. So we have 2 threads. Both perform concurrently read and write on the same variable. Right? If they're running on the same core, the communication time is very short. Right? So if they both are continuously read and write from the same variable, so with at least half chance they will find out the values written by the other party. And in our collocation test, instead of just writing 0 and 1 to the variable, what we did is both threads will put a unique sequence to the variable. So once they not synchronize at some point of time, they know exactly when this happened. On the other hand, if they're running on a different CPU core, the communication time is much longer than the execution of instruction. So when they read from the variable, most likely they will find out the content written by the self. So the data collected from this read and write process will be analyzed using a hypothesis test. So we can easily find out if both threads are indeed running on the same core, or actually they are separated and running on 2 different cores. So in our research, we implement this idea and using LLVM intercompiler. So we compiled those enclave program and instrument the protection code. Again, both threads at the beginning will perform collocation test to synchronize. After that, they can execute their individual task. Also continuously monitor the occurrence of AEX. Once an AEX has been detected, they will come back to run the collocation test again. If succeed, they go ahead with their task. If fail, they will stop. This simple idea turns out to be highly effective and also efficient. And as you could imagine, the performance of this approach depends on the frequency of AEX. So in our research, based on micro benchmark, we found that even when the frequency of AEX as high as 1,000 times per second, still the overhead is just 16.6%. So, and I just showed that the big privacy challenge and for TE could be addressed if we look at some fundamental cause of the problem. We're trying to shut down some necessary condition behind not a single but a set of side channel. Right? Another issue we have to address is performance, because for TE-based confidential computing, always there are 2 questions we will ask. The first is it secure? The second is, does it scale? Scalability is a critical component for practical confidential computing. Today's high-performance computing rely on different accelerators, such as GPU and FPGA. Data processed by those devices, however, cannot be effectively protected without built-in TE. Implementation of chip-level protection could take time. So in our research, we asked whether we could design a technology that offers immediate protection for accelerated confidential computing. Our solution is inspired by today's data center. which pools computing resource and allow them to be allocated to different computing tasks on demand. So in our research, we consider a unique design of a heterogeneous TE, which is a physical box mounted on the server rack to centralize the control of acceleration computing resource to provide confidential computing support on demand. And also the box itself is temporal resistant. That means any unauthorized attempt to open the box to steal the data will cause the activation of self-destruction and the unit inside the box. It will automatically remove all the content inside the data or inside the box. More specifically, inside the high-T box, we have a security controller that manages a set of accelerators together with several high-density microservers called proxy node for performing confidential computing within the box. Those computing resources are collected together and also to be collected to external server node through the programmable PCIe switch fabric. The security controller performs remote attestation and resource management and isolation. The proxy node runs together with accelerator to perform the computation involving sensitive data. Also, for the computing task that only involves public data, they are delegated to other servers on the same rack. So at that point of time, through the PCIe switch, accelerator will be assigned to those servers. And so as if those accelerator were directly attached to the server. At the center of the security control performed by high-T is the PCIe Express fabric, which connects accelerator both to the proxy server inside the high-T box and to the servers outside high-T box. The fabric is software defined and controlled by the security controller at runtime to initialize the switch, configure its routing table, handle errors, hot plug events, and others. In this way, all the hosts collected by the switch only see what the MCPU running on the security controller allows them to see. Also, the switch eliminates the topological restriction of PCIe. Usually, PCI Express network must be arranged in a hierarchical topology with a single path from one node to another. Express fabric allows other topologies such as mesh. When the computing does not involve any sensitive data, the security controller directly links accelerator to the servers on the same rack using the PCIe switch, so the server can use the accelerator as if they were directly attached to the server. And also running this PCIe Express fabric, the high-T could perform isolation in a security mode by connecting a proxy node to a set of accelerator, forming a physical enclave to process sensitive data. When the security controller, MCPU commanded the FPGA to perform secure booting on both the proxy server and accelerator, and prove their initial state to the data owner through a remote attestation. To enclave, if you create, if you have multiple tasks, you can create multiple enclave, each with a proxy node and multiple accelerator. Those two enclaves are physically isolated to minimize their side channel attack surface. Our prototype used two broadband TAX9797 chips to build the PCIe Express fabric backplane. The current high-T box includes two 9797 chips, Y security controller node for proxy node and for NVIDIA GPUs. Both security controller and proxy nodes are implemented as custom boards. And a board now integrates 4 proxy server, which could be extended to 4 servers. The high-T's TCB, trust computing based, is very thin, only including the hardware, firmware, software component of the security controller. Particularly, the firmware on the MCPU is just 1% of the size of a normal Linux OS. Also, the high-T is designed in a way to ensure that most computing resources within the box are shared across the rack. And those accelerator GPU actually are much more expensive than CPU. Particularly when expensive accelerators such as Tesla's high-end GPU are used. Over 95% of expense of the whole high-T box is on the shared resource. So the cost of those dedicated resources such as security controller, proxy node, self-destructing modules actually are very, very small. Our design also provides a set of high-T APIs for creating enclave, for performing attestation, for transforming programs and data to the enclave and getting result back. In our research, we evaluate on TE and using the machine learning model of realistic size, such as VGG16 and ResNet 152. As we can see from slides, for model inference, both VGG16 and ResNet 152 keep a low overhead, and mostly behind 5%. However, for GoogleNet, which has it shows an overhead over 100%. This is because the GoogleNet is very small, so the additional cost incurred by security protection become prominent. However, when it comes to the machine learning training, it's much more complicated than inference. In all cases, the overhead is below 4%. And also for the large network, just like VGG16 and ResNet 152, in most cases, the overhead is below 1%. I just demonstrated that both privacy and scalability challenge in confidential computing could be addressed. Now I will quickly show the application of confidential computing and in a specific area using our iDash competition as an example. In the past 8 years, and we have been organizing iDash general privacy competition. To bridge the gap between privacy and crypto research and the real-world demand for genomic data sharing and computing. The slide is a little bit old. It does not include the most recent competition. Our competition has been extensively reported by Nature News and the JournalWeb. It has also become a benchmark for the research on different kinds of confidential computing technologies. Starting from 2014, only 33 teams participated in the competition, with differential privacy-based and data sharing and secure release as 2 tracks. And in I think 2019, we have 21 countries participating in the competition. We have 4 tracks, including a TE tracks. So in more recent years and before pandemic, we usually have more than 100 teams around the world to participate in the competition. During the pandemic, the number goes down a little bit. Now it goes up again. And using the competition 2019 as example, and we challenged the competitor to run a deep learning model of 200 megabytes, which is for predicting response of breast cancer treatment. The model were trained on the real breast cancer patients' data. And the model is supposed to run within the SGX enclave to ensure its accuracy and also improves the performance as much as possible. As you could see here, the winning solution fully preserved accuracy, but the performance was still relatively low, about 1 second for each inference. With the availability of large and protect memory size for Intel's SGX, and this performance bottleneck has been addressed recently. And also with the availability of GPU-T as proposed by NVIDIA, and we believe down the road, and the dream of accelerate confidential computing and could come true, and the confidential computing and will become truly scalable. Before the end of my talk, I would like to quickly introduce the newly founded Center for Distributed Confidential Computing. It is the largest investment from National Science Foundation on confidential computing. The CDCC aims at laying the foundations for large-scale, fully distributed confidential computing and supporting a set of transformative applications. For example, confidential autonomous driving that ensure all the driving data gathered from a driver will only serve that driver, and confidential anti-money laundering that ensure complicated machine learning models could be used across banks for detecting criminal activities without exposing customer transactions to the other bank. Our vision is to create a research, education, knowledge transfer, and workforce development environment that enables scalable, practical, verifiable, and usable data in use protection on today and tomorrow's cloud and edge system for the purpose of establishing U.S. leadership in AI and data science that rely heavily on data in use protection. To that end, we organized an interdisciplinary team with 10 PIs from 8 universities. The principal investigator of the project have extensive experience covering all related research areas. Some have made seminal contributions to related cybersecurity research, such as access control, side channel, TE, blockchain usability. This interdisciplinary team will work together on a highly integrated, ambitious research agenda, including both fundamental research on the building block of distributed confidential computing and use-inspired research driven by transformative application. The 3 transformative applications we started including data in use protection for IoT cloud edge system and autonomous driving. The second is privacy-preserving collaborative anti-money laundering, and the third one is confidential disease prognosis. Those transformative applications will be built on top of foundation. And in the meantime, the unique challenge they introduced will enable use-inspired research to improve and to improve the foundation. The foundation contains 4 interdependent and also complementary building blocks. Assurance of TE code that certifies the security property of TE programs for enforcing data use policy. Assurance of TE node that specifies the policy and verifies the enforcement of the policy by certified program running in a TE node. Assurance of TE workflow that verifies the whole workflow to be policy compliant, and assurance for stakeholder that supports the usability of all technologies to be developed. And also research is only one piece of the puzzle. The center will also take the lead in confidential computing related education, workforce development, and broadening participation. We plan to develop the first confidential computing curricula and make it a model nationwide and even worldwide. We will work with minority-serving institutions to train students from underrepresented groups on distributed confidential computing. We will also aggressively seek technology transfer with industry partners and work with them to develop a qualified workforce. Our objective is to join our research, education, and outreach effort in such a way to induce a domino effect. A diverse and well-trained workforce will produce better research outcomes, which could lead to more technology transfer and better products. Practical distributed confidential computing product will transfer computing, enabling effective use of data without revealing its content. For example, and we could imagine in the future, and we will still have a target advertising to promote a most suitable product to you. But in the meantime, we can guarantee, we can provide assurance those ad company will not access to your personal information. And this could lead to a profound impact, arouse greater public interest in the technology itself, and therefore attract more talent to do research on distributed confidential computing. Okay, finally, let's discuss what's the next big things for confidential computing. So there are a lot of big research questions, a lot of research problems can be studied in this domain, right? But most importantly, I'm going to talk about how to narrow the trust gap between trust execution environment and a crypto solution. A crypto solution still needs to trust the hardware running the crypto software that does not contain any Trojans. But in the meantime, any crypto solution will not entrust its root secret to hardware manufacturer. Unfortunately, that's not a situation for TE. In today's TE design, you still need to trust those hardware manufacturer to keep the root secret. So down the road, I believe that a new TE design needs to move the root secret out of the hands of the hardware vendor and give the authorized user full control of the system. Also importantly, all crypto solutions can be proved, although the proof of a security guarantee is based on some assumption about a hard problem, right? But at least there's something there. But today's TE design is opaque ad hoc, right? So to gain the public trust in TE, the future solution also needs to be fully verified. And also the whole process needs to be transparent, needs to be open, right? So the verification needs to happen not only on the design, but also on the implementation to gain public trust on the security assurance provided by the system. So I believe only in this way, we will be able to reduce the trust deficit of trust execution environment, so its performance advantage could stand out. This will bring us to a new era of data in use protection, in which individuals' personal information could be shared freely, and all such information could be collected extensively for the purpose of providing the best possible service to the user. But in the meantime, we have the assurance that our personal information could not be abused. And how the data will be used will be fully verifiable. And there's guarantees that information can only be utilized in a way that fully aligns with the data owner's interest. And I believe, with the maturity of the confidential computing technique, with the continuous effort in this area, that day will come. And thank you. That's all my talk. So thank you for your attention, and I will be happy to answer your question.